Hey everybody, welcome to the third video in this series on linear relations. We're going to be talking about patterns in a table of values. At the end of this lesson, you should be able to identify relationships in tables of values, how to decide whether or not they form a linear relationship, and also how to use the table of values to graph a line. Okay, so let's start off here and whoops. We're going to start off by talking about patterns just in general. We have Aaliyah's tiling her bathroom floor, and she's got this pattern that she's making. And we are going to take a quick peek at what this design is, what kind of patterns there are, what kind of relationships between those patterns. So first, what are some patterns that you see in this design? Well, I definitely see that there are squares, and the squares are repeated from one to the next. There are also triangles. There's a pointing upward triangle and a pointing downward triangle, and those are repeated as well. You could also break it down further and talk about, which we will, vertical lines, horizontal lines, oblique or slanted lines, and so we will talk about that. How many squares and triangles are there in this completed design? In total, there are 8 squares. And there are 16 triangles. I'm going to include both here, upwards and downwards. The design is made up of 8 sections, so we're calling one of these a section. So one section would look basically just like that, but not as bad as me. All right, so this is one section. Are there any patterns in this design section? Yeah, we talked about that already. We got the triangles, 2 triangles for every 1 square. We can also talk about the vertical lines, the horizontal lines, the slanted lines. All right, we can break it up. We're going to create a table of values really quickly from that design. So let's say there's 1 section, there's 2 sections, 3 sections, or 4 sections. The number of vertical segments. I'm going to have to draw this out really quickly because it'll make it a little easier to see. Unless my drawing sucks, which it kind of does, but we're just gonna have to go with it. All right, and there we go. All right, so we have 4 sections here. Number of vertical segments in one section. If there's just one section like this, we have 2 vertical lines. Okay, and if we were doing 2 segments, so these 2 included, we'd have 1, 2, 3. They share 1, so we'd only count that once. And then number 3, 1, 2, 3, 4. So notice it's going up by 1 every time. It goes from 2 to 3 to 4 to 5. Number of horizontal segments. So horizontal is sideways like this. We've got 1, 2, and then we've got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So it's going up by 2 every time. It's not a G, that's a 6. And 8. Number of oblique, that means slanted. So we've got 1, 2, 3, 4 for one section. And then it seems to go up by 4 more. So 4, 8, 12, and then 16 finally. And we've got the same thing just written out here, a little bit nicer than what I have. We have some graphs here that we can use. And what I want to point out here is the lines that we're making, the graphs that we're making, are based on a relationship between 2 different things. So we could say the number of sections compared to the number of vertical segments. We could also say another graph. We could also make another graph of number of sections to horizontal segments, or the number of sections to the oblique segments. We could also compare vertical segments, horizontal. We can really compare anything, but you're choosing 2 things. So we're going to start off with just the number of sections, and that's going to go here. So number of sections, and we're going to compare that to the number of vertical segments. So number of vertical segs. All right, and these are going to be my x values, and these are going to be my y values. All right, so if I was going to plot these points, I'm looking at these right here. Then my first x value would be 1, and it would meet where y is 2. So 1, 2. I've got a point right here. And then I have 2 and 3. So 2 and 3. Then I have 4 and 5. Wait, sorry, 3 and 4. And then 4 and 5. Okay. So you see it is kind of making a line right along there. It just goes up by 1 every time. That's perfect. So that's really what we're going to be doing. Describe in words the relationship between variables. I kind of did that already. We're just comparing two different things and talking about how one grows in relationship to the other. So in this case, we have for every increase of one section, we have an additional one vertical segment. Okay. That's not the case for the other ones, though. For every increase of section, for example, here, let's try the number of horizontal segments. So number of horizontal segments. For every increase of 1, we are increasing by 2. So 1, 2, 2 to 4, 3 to 6, and 4 to 8. Okay, so it's increasing faster. It has a higher slope. So we would describe the words using the relationship between the two as being a little different. So for every increase of section, the horizontal segments increases by 2. What is the expression for the number of vertical segments in terms of the number of segments? I think that's supposed to say sections. So that's the first one here. The expression is, so the number of sections, and it starts with 2, right? And then for every section, it increases by 1. So what I could really say is, I'm going to call this, okay, so this is my x variable, and this is my y variable. So my number of sections is x, all right, and then it's basically just x plus 1, because it starts off with an extra 1 at the beginning. So that, just to show you, if x was 1, then my y value would be 1 plus 1 is 2. If my x was 2, then it would be 2 plus 1 is 3. So it's just x plus 1 is what my y would be. I'm going to quickly just do the other one too. Here we have the number of horizontal segments, and what I notice is that it doesn't start off with an extra number, but it goes up by 2 every single time. So in this case, it would be the number of sections times 2. So just 2x. If x was 1, then it's 2. If x was 2, then it's 4. If x was 3, then it's 6. Okay? So you're just looking at the expression that shows the relationship between the two. And you can always test it with your table of values just to find out if it works. Okay, move forward. This is just a pattern, and what we could do is look at a segment here. And there's a lot of different ways that we could look at it. We could look at one segment compared to each individual pieces. So that's really, one segment is 3 pieces, and 2 segments is 6 pieces, 3 segments is 9 pieces. We could also look at the different kinds of lines, horizontal, slanted. There's a lot of different ways that we can look at the relationships here. There's not much notes or anything to take here. I just want to point that out, that we could look at segment versus horizontal lines. Or we could look at segment versus slanted lines. We could look at segment versus the pieces. Pieces. And by pieces, I mean that. Okay? Although not as horrible. Here's another example. We have the square here with the half circles all around. We could look at many different things. We could compare the entire thing. Okay. Wow. I'm not really an artist today. So we can compare the entire thing versus how many squares there are. We could compare each segment to however many half circles there are. I keep saying segment, but I mean segment or section. So this is 1, this is 2, this is 3, this is 4. We could also compare to horizontal lines. We could compare to vertical lines. There's a lot of different things we can do. Remember, the purpose is the relationship between two things. Okay, now we get into graphing with a table of values. So we are going to determine the difference in values for the consecutive x and y values in the table below and then graph them. All right, that sounds really scary. It's not. I'm going to tell you all the individual pieces that will really help you first find out whether something is linear and then how to graph it. First question here is, what is the vertical distance between points? Remember, vertical distance is going up and down. So that would be your y. Your x is your horizontal. So here's my vertical, and here is my horizontal. Okay? And if I'm talking about the distance between points, I just compare them. I look at this first one. From 1, it goes to 4. So what's the jump from 1 to 4? Well, 1 plus 3 is 4, so it jumps by 3. How about 4 to 7? 4 to 7 jumps by 3. How about 7 to 10? By 3. 10 to 13? By 3. Notice that they're all the same. That's important. And then you can also look at the horizontal jumps. It goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4. Those are all jumping by 1. Okay? So the vertical distance between points is 3, and the horizontal distance between points is 1, and it doesn't change. Because it doesn't change, it is a linear relation. Yes, it is. Okay? Let me quickly plot the points here. So I have x and y. That makes the point 0, 1. So 0 and 1. Then I have 1 and 4. 1 and 4. 2 and 7. 3 and 10. I'm going to run out here because my graph doesn't go large enough, but 2 and 1, 2, 3, 4, 5, 6, 7. It is a linear relation, and I'm not going to be able to draw the next point, but it will be somewhere up like here, and then it'll extend off my screen, and it'll just form a nice line, nicer than that. But it is a linear relation, so it works out perfectly here. Here we go. Here's another one. So we're going to look at the jumps. Even though we're starting with negative numbers, it increases by 1. Negative 2 to negative 1 jumps by 1. Another 1, another 1, another 1. So the horizontal distance between all the points is 1. Easy. Now look at this. Y goes from 6 to 4. That's negative 2. It removes 2 from 6 to get to 4. Does the same thing here. Minus 2, and minus 2. So the vertical distance between points is, well, it's 2, but it's going down by 2. Is this a linear relation? None of these change, none of these change, so yes. Okay? And I'm going to clarify something here. I'm saying none of them change. They're all steps of 1 and how much it goes. I could also have done this. Let me just point something out for you. This goes 1, 2, 4. And yes, that is a step of 2. Okay? But it will still be linear if this is minus 6, because although that jump here is going from, it's not like continuing minus 2, minus 2, minus 2. It is continuing minus 2 for every step of x. Well, my tongue is getting twisted here. So I know that if it goes 1, 2, 4, then since this is double stepped, then that one should be like minus 2 twice, because we would have 3 and minus 4 in between. It's kind of tricky, but it looks a little bit easier when you graph it. So let's try graphing. Minus 2 and 6. So minus 2 and 6 is right here. And then minus 1 and 4. We have 0 and 2. We have 1 and 0. And minus 2. Okay? So we have this line that goes straight through these points. Hopefully my writing is a little easier to read this time. Okay. So we would expect a point here, and we would have expected a point, I guess, right here. Okay, and that would be 3 and minus 4, and 4 and minus 6 if it was continuing that trend. So even though I did, in this little example I added on, even though I did jump an extra, remember that we're looking point by point whether it continues to be straight, whether it continues to change in the same amount every time. That's important. So don't rely on just your graph. Okay, make sure that the change in points is the same. Okay, here's another example, and then I believe you have, your own show you knows that you need to do. Wait, what happened? Oh, they're out of order. Okay, so let's do this. -8, -15. I'm not going to be able to graph that. My graph isn't good enough. But let's start with -4 and -7. That's going to be right here. I'm jumping ahead. 0 and 1. 4 and 9. 4 and 9 is out of my screen. So my graph isn't a really good graph for this. I should have probably made each one of these 2 or made it a larger graph. But we should be able to tell the vertical distance between points and horizontal distance between points and linear relationship just from the table of values, really. So this is changing by 4, and this is changing by 4 and 4 and 4. So none of that changes, so I don't have to worry about that thing I did in the last one. So if none of these are changing, then none of these steps should be different either if it is linear relation. Okay, so -15 to -7 jumps by 8. -7 to 1 also jumps by 8. 1 to 9 by 8. And then 9 to 17 also jumps by 8. So for every increase of 4x, it goes up by 8 every single time. So that's perfect. So horizontal distance is by 8, and vertical distance between points is by 4. But we're talking about between individual points. So this is like 4 to 8. That's not really what we want. We want to know for every individual point. And you can also look at it like a fraction, like 4/8 is really the same as 1 to 2. Okay, so the vertical distance between points, do I have these backwards? I have them backwards, my bad. So it should actually be 8 to 4 and 2 to 1. So for every increase of 1x, it's actually an increase of 2y. And let's check that out. For every increase of 1x, it goes up by 2y. If that's true, these will make sense. Step, 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 step. And yep, it matches up. Okay? And a line will form between these points. And there we go. Okay, so is this a linear relation? Yes, it is, absolutely. I already showed you the answer. But try this out. Show you know. What I want you to do is the same thing. Find the vertical distance, horizontal distance, graph it. You can just sketch it on a paper and make it work out and find out whether it's a linear relation. So because it's a show you know, pause the video now, try it out, and then I will show you the answer. Okay, so here's the answer. It steps by 1 every time, and then it steps by 2, 3, 2, 2. Notice that 3 there. That 3 is a problem. That is showing me that it increases by 3 where I would expect it to increase by 2. So it's not linear. They should all be the same if it were. Okay, so that one right there, this is a problem. So on my line, I didn't graph it perfectly again, but these dots are all linear, but that one right here kind of throws it off. It should not be there. Okay, so no, this one is not a linear example. What conclusions can you make about linear relations in terms of the pattern you may see in a table of values? Think about that one for a minute. Well, the conclusions that I can make in a linear relation is if something is linear, it has a very predictable pattern. Like in those patterns for the tiles. I know how many of each piece there will be when I'm building my tiles. So linear relations are predictable, for sure. So there's some predictability there. Oops, predictability. What else? What conclusions can you make? You know what the increase is, you know what the decrease is, and you know that they have a relationship that is unchanging. It's always going to be the same. When this increases by this amount, the other one will increase or decrease by this amount. And that's where that predictability comes in. Linear relationships are nice and easy. Okay, we're at the last couple things here, and I'm going to show you an online tool that should help you since you're at home and you don't necessarily have the same paper materials as usual. So, do these ordered pairs represent a linear relation? We're going to look at each of these separately. Here's one, here's another, and here's another. So, in this first one, -2, 9, and so on, you would do this a couple different ways. You could either create a table of values like I did and just look at the steps. You could also graph them and see if it does form a predictable line. What I'm going to show you is how to use an online tool just for graphing, for using table of values and that sort of thing. And right now, let's see if I can switch my screen over. Screen share setup. My screen should have changed for you, hopefully. And I'm going to switch my screen over to this one right here. So if you go to a website called Desmos, desmos.com, and you click on, let me just go there real quick, desmos.com, you click on Start Graphing, it will bring you to this page here. And on this page, you can do a number of really interesting things. But for now, for your purpose, table is what you're looking for. So what we're going to do is we are going to use that table of values. Oh boy. We're going to use that table of values here to create a graph. So I'm going to enter all these for you. -2 and -1, 0, 1, and 2. And then I'll match up my y values here. I've got 9, 6, 3, 0, and -3. Now if you look at my graph that I've created here, let me make it a little better here, you'll see that they do kind of match up in a line, right? It does look like a pretty perfect line. And if I put a line through those points, they would match up exactly. And I can double check just by looking at my table of values. For every increase by 1 of x, it decreases by 3, and it matches all the way through. So yes, that one is definitely linear. Let's go back to this. We have -5, 9, -4, 11, 3, 13, -2. Okay, so let's try this one out. I'm going to make a new one here. That's -5, -4, -3, -2, -1. And in my y values, I've got 9, 11, 13, 15, 17. Okay, just by looking at the table of values, it's increasing by 1x every time, and it's increasing by 2y every time. So yes, that's linear. I already know that. But let's see what the graph looks like. The graph looks very linear as well. If I put a line through all those points, it would be linear. And let's do the last one real quick. I've got, x. All right, so 0, 1, 3, 4, and 5. You can't see it. It's off my screen a little bit, but that's okay. I'll bring it back up in a second. -5, -2, 1, 3, and 6. Okay, so I've plotted all those points. And if I zoom out, I will see, oh, wait, these are kind of weird. I've got a point down here, then I got a point up here, and then it kind of jumps over here, and I've got another one here, and another one here. If I stretched a line through this, if I chose like 2 points and I put a line, it would go like, or might go through here, or it might go, yeah, these don't match up. They're not linear. And if I look at this one jumps by 1, then it jumps by 2, so I would expect that the change would be double. But it's not. They don't match up. So that does not work out too great for me here. Okay. Yeah, I don't need that one for now. Let's go back to this. Here you have a show you know. So this is the point where I want you to play around with Desmos. So I want you to go to desmos.com/calculator. And I want you to try these table of values. And just from looking at the graph, I want you to tell me whether you think it's linear, and then check it versus your table of values. You can pause the video now. Okay, I'm going to go over to mine, and the first one I've plotted here. Let me just zoom out here. Okay, that looks good. So does this look linear? That does look linear to me. I would say so. If I stretch the line through here, so let's see, it goes like that. Yep, that is a linear example. Let's check the next one. The next one right here. That one, just looking at it, I can already tell that something is wonky. This dot right here doesn't seem to match the pattern of the rest. Actually, this one doesn't either. Those two seem a little bit off compared to the other one. So if I stretched a line through these points, that would be a little bit too high, that would be a little bit too low. So the second one does not work out. How about the third one? The third one, is it linear? That one's a little tougher to see on the graph. I can't tell perfectly just by looking at it whether it is linear. That is really difficult. So in this case, I might have to look at my table of values. And in my table of values, I've got 1 to 5, that's an increase of 4. And then I've got 5 to minus 2, that is a decrease of 7. So these are not arranged in a very nice pattern, are they? It would probably be easier if I had instead gone minus 5, minus 2, and then 1, 3, and 5, and then match those up. So let's, whoops, minus 258, that's not right. Let's check that out. Minus 2 is minus 13. 1 was minus 1. 3 was 7. And 5 was 15. I'll erase all the others. Okay. The reason I did it like that is because now I can check in my table of values how much each increase is and whether it matches up to the rest. So I can compare going from minus 5 to minus 2. That's a step of 3 up, or 3 to the right. And then minus 25 to minus 13, well, that is a change of positive 12. Now, if I look at positive 12 and a step of 3, then that means for a step of 1, I would expect 4 up, right? Because 4, 8, 12. So each one of these, for every one step, should go up by 4. Now I can look back at my graph. This is 5 to minus 25. Oh, I need to zoom in because that is why it's looking a little weird for me. Let me go here. So for every one step over, I go 4 up. One step, 1, 2. Oh, let's make that nicer here. That's 2 minus 13. Okay, so for every one step to the right, which is here, I go up by 4. So 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. Yeah, it's not matching up. It is not matching up. Or I'm just having trouble with reading Desmos because of my zooming function, because I've got really bad ones. So let's see, what would I expect? I can actually put new plots in from what I would expect. That might be a better way to do it with Desmos. So let's try that. So if it was minus 5, then minus 4, if it was the same step, it would increase by 4, so it would be minus 21. Here's a smarter way for sure. Minus 3, that would now be minus 17. So minus 2 should be minus 13, which it is. Minus 1 should be minus 9. And then 0, I would expect it to be minus 5. 1, I would expect minus 1, yes. And then 2, I would expect positive 3. And 3, I would expect positive 7, which I do. And 4, I would expect 13. 5, I would expect 18. Oh, so actually it was really linear up until the point right at the end where I got to 5 was supposed to be 15, but it was 18. So these ones, 4, 13. Oh, did I mess that up? 4. Oh, I messed it up. See? I'm the one that messed up. And that's one thing that's really nice about Desmos is you can actually see visually what's happening to your table of values, whether you type something wrong or what. Now it is linear. If I look at all those points, that definitely looks a lot better. I know that one took a little bit longer, but it's nice to be able to play with a tool and really see things in action. Okay, let's go back to here. I'm going to switch my screen again. There we go. Okay, so do they represent linear relations? Yes, no, and yes. I think that's what we found. Yes, no, yes. All right, do these sets of ordered pairs represent a linear relation? I have different screens here, so we're going to do it a different way. We're not doing Desmos now. We're going to do it by hand again, and we're going to see whether we can use that strategy to find whether they represent linear relations. Okay, here's the first one. 7, 3, negative 3, blah, blah, blah. I'm going to do that same thing I did before. I'm going to do them in starting with the smallest x and then increasing from there, just so it's laid out in a nicer way. So my smallest x is minus 3, 7. So I'll do that one first. Minus 3 and minus 7. Then I have minus 1 and minus 5. And then I have 1 and minus 2. Then I have 7 and 3. Okay. Now I can look at the jumps. So that one jumps by 2. And then it jumps by 2 again. And then it jumps by 6. Okay, and that's fine if it jumps by 6, as long as that same number of steps, the same, you would expect to be 2, 2, 2. So that's actually like 3 times more of a jump. So it's actually 3 major steps that happened here, and I would expect the same thing to happen to the y, if it were, linear. So minus 7 to minus 5. In terms of a vertical jump, I go up by 2 for every 2 steps. And then here, I go minus 5 to minus 2 while I'm changing by, that's 2. Then minus 5 to minus 2, that's a change of 3. Not what I was expecting if it was linear. All right, so then minus 2 to positive 3, that's a change of 5. I can already tell that there's something weird going on here if this is supposed to be linear. It is not linear. Let's find out. Let's start graphing. Minus 3 and minus 7. Minus 3, minus 7 is right here. Then we have minus 1, minus 5. Minus 1, minus 5. Then we have 1 and minus 2. 1 and minus 2. Then we have 7. 7's all the way here. And positive 3 is right here. So, yep, that is not linear because if I stretch the line through here, it's not going to match up to all the points. The changes are not equal across. Let's try the next one. We have minus 2, minus 4. Minus 4 is the smallest, so let's go, let's try that again. Minus 4 and minus 12. We have minus 2 and minus 6. We have 1 and 3, we have 3 and 9. That's a change of positive 2. That's a change of positive 3. That's a change of positive 2. This is okay as long as the change for every one x is the same all the way across. This is the stuff that really matters right here. So this changing by 2 x's increases by 6. Changing by the 3 x's here, so going from minus 6 to 3, changes by 9. And here we have 3 to 9, and that's 6. So that looks like for every 1x, it seems to be changing by 3y. Yeah, it does seem to actually look linear. Let's try it. Minus 4 and minus 12 is going to be way down here somewhere. I can't plot it. But let's look at the next one. Minus 2 and minus 6 is right here. And we have 1 and 3. And then we have 3 and 9 is going to be up here. So it does look like for every 1 over, it goes up by 3. 1 by 3, 1 by 3. This one is linear. Okay. And I think we're just about at the end here. I'm going to do one or two more and then we're done. I know it's a little bit longer. I want to cram as much as possible into this one, and then there'll be one after. Let's see, show you know. So read through this one, pause the video, and give it a try. All right, so you should have had a chance to work through this. I looked at each of the individual steps and I wrote all my notes up here. These ones increased by 3, and then the change from the B line here goes up by 9. So yes, this is linear. All changes are reflected in the same way. The next one, table 2, goes 1, 1, 1, and then 1, 2, 3. So for every one change in P, it doesn't reflect the same increase in Q. So when we plot them, it will not be linear. So yes, linear for table 1, no, not linear for table 2. All right, we're near the end here. We're just going to analyze a little bit of data. So this graph shows Nicole's rate of pay based on the number of hours she worked at her part-time job. So just looking at this graph, we have to see a few patterns. First, her time is reflected in the bottom. Her pay is reflected vertically. So for 1 hour, she earned $10. For 2 hours, she earned $20. For 3 hours, she earned $30. Already, you could see that this is linear. For every 1 hour, she gets $10. She gets $10 per hour. And that's the question for B. What is her hourly rate of pay? Well, I can already tell it's $10 per hour just by looking at these steps. For one, I should draw it the other way actually. For one increase of hour, it goes up. Her pay goes up by 10. 1, 10, 1, 10. Okay, so that's $10 per 1 hour. Table of values from the graph. Okay, fine. I could write 0, 0, but that's not a very good example here. But I could write, instead of X, I'll have H. Instead of Y, I'll have P. Wait, it's not X. It's not H. It's actually T for time and P for pay. That's what they wrote. P and T. All right, so for 1 time, 2 time, 3 time, and 4 time. And those are in hours. And her pay is 10, 20, 30, and 40. Okay, so we've done this, this, and this. Is it possible to have points between the ones on the graph? I don't know. I would think that most jobs would say, no, you need to work a full hour. Your hours are this to this. But that really depends on her job. They might say this is your hourly rate of pay, but you can work a half-hour block. So yeah, I guess it's possible. She could work 3.5 hours and they will pay her $35. Sure. I mean, it's possible. It depends on the job, but yeah, it's possible. Why not? Okay, here's a show you know, and I believe this is, yep, the last one. So Chad is buying notebooks at Bob's Bargain Store. I think we've looked at this one before. Describe patterns you see on the graph. What's the cost per notebook? Make a table of values. And I'll fix this already. So this is N and this is C. And then is it possible to have points between the ones on the graph? Go ahead and pause the video and try that last one out. Okay, here are the answers. So if I'm replotting these, I've got N and C. For every one notebook, it seems to increase by $2. So that means that I have $2 per notebook, and that's the cost here. $2 per notebook. Patterns that I see on the graph, it's definitely linear. For every increase of one notebook, it goes up by 2. And that's really what the 2 per notebook is. Table of values is right here if you need to double check that. And is it possible to have points between the ones on the graph? In this case, no. You cannot go to Bob's Bargain Store and buy half a notebook. They won't sell it to you. They wouldn't have included it in their stock. It's not reasonable. So you cannot buy a third of a notebook. You cannot have these points. There's just 1 notebook, 2 notebook, 3 notebook, 4 notebook. It has to be a complete notebook or they won't sell it. So now we are finally at the end of this one. We can stop, and when you're ready, you can move on to the next video.